Okay, good afternoon and welcome to MAE 106. This is Discrete Mathematics with Probability. My name is Richard Kohar and this is lecture 21. And in today's lecture, we're kind of doing a summary. What we're going to do is kind of just a general approach, to solving counting problems. Good afternoon. Good to see that everyone is in on this 2nd of November 2021. So, throw that pen away. Okay. So we've done quite a few different kinds of problems. We've done problems where the order matters and where the order doesn't matter. We've done it where there's repetition, where there's no repetition. We've done some where we're picking objects, some of them, all of them. And what we're going to do is we're going to just come up with a little chart to kind of summarize everything. So if we have a counting problem, kind of the first thing that we will pick or kind of ask ourselves is, does it matter if there's order? So if the order matters, or if there's no order. So what happens then is, if the order matters, we're kind of thinking permutations. So if there's, let's say, no repetition, so we're still thinking kind of like permutations in this case. There's no repetition. Then there's another case that we kind of drop down in, and it's where they're all distinguishable. Oops, let's see. Distinguishable. So in that case, we're dealing actually with just that permutation. So we can do it as P or n permute R. And we know what that formula is, which is n factorial over n minus R factorial. Now, okay, so we can have order matters. There's no repetition, but we can have where some objects are alike. And then in that case, we switch over to using, we had the n factorial and we divided by, say, n1 of alike factorial, n2 alike factorial, all the way up to n sub r factorial. And so we had a short form of writing this. We had n factorial over n1, n2, and nr. So we did that in the previous lecture. Over on this side, we have the order does not matter. And this is where we can pick exactly our objects. So for that, we can use, so this is a combination. So we can actually just use that binomial coefficient. So we have n, choose r. This isn't on the test. What's on the test is assignments 4 through 6. And so on the test, there can be some simple counting questions. On the test, it will have the pigeon principle, it will have the sum principle, and the multiplication principle. That's right. Lectures 12 through 17. Okay, so we can have the order doesn't matter. There's exactly our objects. There's also one where we had done where it was all the possible subsets. And for example, that was where, let's say they were all distinct. Something like sandwiches. That's a good question. I'll get to that. Somebody's asking, is n permute r equal to n factorial over n minus r factorial, r factorial? No. Because in that, it's actually this one. This is the combination. This is different because this is what we call the combination. And over here is the permutation. And the reason for that is we have to divide by this r factorial because we are overcounting. So when the order doesn't matter, we need to remove some of the overcounting that we're doing. But I can show you something in a second. So if they're all distinct, for example, like we had the sandwiches. If you had 3 toppings on a sandwich, then we knew that it was 2 to the 3. So in this case, for us, it's 2 to the n. If you had n distinct objects. So yes, we have n permute r is n factorial over n minus r factorial. So this is called the permutation. That's usually what I refer to it as, the permutation formula. And over here is the combination formula. Combination slash binomial coefficient. Okay. So here's a question, which is, a permutation n permute r equal to n choose r times r factorial? Well, if we start with the right-hand side, I have n choose r times r factorial, which is equal to, by definition, n factorial over r factorial n minus r factorial, which is equal to times r. This cancels, so that I'm left with n factorial over n minus r factorial, which we know is the definition of n permute r. So yes. So that's the relation, is that you can have a combination and then we need to multiply by all the possible orderings of it. So remember, when we're doing combinations, that I have, say, 1, 2, 3, 3, 2, 1, 1, 3, 2, 2, 1, 3, 2, 3, 1. So there's 1, 2, 3, 4, and I know, and there should be one more. Three, 1, 2. That if I said 3 choose 3, that would give me 1. And then I need to multiply it by r, which is in this case 3, so that would be 3 factorial. So 3 choose 3, there's only one way to do that, times 3 times 2, which gives me 6. Or I could think of it as 3 permute 3, which is 3 factorial, which is the same as 3 times 2 equals 6. Okay. Okay. Here's something else to brush up on our algebra skills. solve for n, where n is a natural number. And we're going to say that we're going to have n choose n minus 2 equals 28. So to do that, what we can do is we can substitute in our formula for it, which we know up here, which is n factorial over r factorial, n minus r factorial. So up here is n factorial. And then we have our r, which is n minus 2 factorial. Then we'll have n minus 2 factorial. So you'll have n minus n plus 2 factorial. N minus n is 0. So then I'm left with n minus 2 factorial to 28. So what I can do is I can bring this 2 factorial over to the right-hand side, so that's multiplied by 2. And over on the left-hand side, I'm left with n times n minus 1, n minus 2 factorial. This cancels. So I have 28 times 2, 56. And then I'm left with n times n minus 1. So expanding that out, I get n squared minus n equals 56. And what I can do now is I can actually factor this. So these are skills that you would have seen in 103. So we have something like this. We have something that needs to multiply to give me 56. It needs to sum to give me minus 1. And so the two numbers for that would be minus 8 and 7. So again, the minus 8 plus 7 gives me minus 1, and then minus, oops, and yes, sorry, I looked up. And the minus 8 times 7 gives me the minus 56. So therefore, it's n is either minus 8 or 7, sorry, plus 8 or minus 7. Just because of solving this. Now we know that because n is a natural number, it can't be less than 0, so this is it. So therefore, n equals 8. So just as a quick check then, I would have 8, and then 8 minus 2 is 6. So 8 factorial over, didn't you have it right the first time since it's minus n? Oh. So to solve this, so I have n minus 8, n plus 7 equals 0. So this means that I have n minus 8 equals 0, or over here, n plus 7 equals 0. Right? So for this to equal 0, for this to satisfy this equation, that one of these has to equal 0. So it could be that n minus 8 equals 0, which would be 8. So 8 minus 8 would equal 0, which would make this whole thing 0. Or I can have minus 7 plus 7, that is 0, which would make this whole equation. Okay, perfect. So what I can do over here, okay, then I have 2 factorial, so let me just write that out. So 8 times 7 over 2, that 2 goes into the 8. So 8 divided by 2 is 4. 4 times 7 is 28, which is what we wanted. Okay, so let's try this one. So let's say if there are 8 points, if 8 points arranged on a circle, then how many different ways can the 2 points be joined together to form a line? So what they mean by this I have a circle here, and they say I have 8 points, okay, so again, this is one of those things where drawing a diagram helps. Because if you don't know what to do with the problem, sometimes a visual aid can help. Okay, so we have 8 points. 1, 2, 3, 4, 5, 6, 7, 8. They're on the circle, and we pick 2 points, and we're going to join them together to form a line. So something like, I don't know, you could pick this one and this one. And that's it. And they say how many ways. Okay, so if we're going to use our counting problem kind of algorithm, we have this. The first thing that we should ask ourselves when I'm picking these 2 points, does the order matter or does the order not matter? What do you think in the chat? That's right. It does not matter. If there was some sort of direction, yes, if there was some sort of direction, then we would have to say yes. But because it doesn't matter what direction the line is going, we'll say no. Okay? Number 2. Am I selecting all objects or just some of them? Okay, so am I picking all the points or all the possible subsets, or are we just picking exactly our many objects? Just some of them, exactly. So we're picking some of them. Two at a time. Which means that we're leading to this one, which here is a combination. So we'll use this formula, which is n choose r. So this leads us to a combination. So that's n choose r, which is n factorial over r factorial over n factorial over r factorial n minus r factorial. Yes, we're going to be using all of them, but so so in this case, we'll have, there's 8 points and we're picking 2. Yes, and Mr. Perry is already picking out that it should be the same answer. And why is that? Well, by symmetry, he's noticing that it's 8 minus 2. Because he's saying here that this is equal to 8 points. And we don't select 6 of them. So that would be 8 choose 6, which we had done previously, which was up here, which was 8 choose 6, which was 28. Now, Now again, if you don't believe me, there's the 8 choose 2, which is 8 factorial over 2. 8 minus 2 is 6 factorial. 7 times 6 factorial. 56 over 2, which is 28. And again, just as a review then, that's called the symmetry property. And we had covered that previously when we were talking about combinations, but if I had 8 objects and I pick 2 of them, it's equivalent to me saying I have 8 objects and I don't pick 6 of them. So we should finish this off. So therefore, there are 28 ways to pick 2 points on a circle to form a line. Okay. Here's one. So we have 6 signal flags. Can be selected to fly on a ship's flagpole. And what we're going to say is we're going to say 6 different. So they're all distinct. How many different signals can be made? Using at least 2 flags. Okay, so this is using at least 2 flags. So then the question is does order matter? Does it matter or does it not matter? Okay, so you'll have to, So you'll have to tell me how it is in real life. Does the order matter? A bit. So if I had like, I had a green flag and I had something like that. So you're going to tell me that if it was a signal that these two would be the same. In real life, pretty sure the order of flags matter. Okay. It matters in the same way that the order of words. Not in real life. Okay. So it ultimately comes down to how you interpret the question then. So what we would say is that, let's assume that these mean two different things. So that means then if I assume this, that these, if I change the order, then it would mean something different. So let's say yes. Is everyone okay with that if I say that the order does matter? Mine was an autocorrect, not bit. Okay. Okay, so the order does matter. They're all distinguishable. Everyone's like, yeah, that's okay. Good. Say yes. Then kind of tracking with our chart, we have the order matters. There is no repetition. We'll say that they are all distinguishable. Then we can use this formula. So this is leading us to that it's a permutation. And that we should be using n permute r equals n factorial over r factorial over n minus r factorial. Oops. Pay no attention to that. Okay, there we go. So now where we have to think a little bit more, we know that it's a permutation, but we have a little bit of a complication because it says at least two flags. So this means that we need to take cases. Because you have the sum principle at work. Because you could have two flags or three flags or four flags or five. Do you see where I'm going with this? Or six flags. So I have six cases. So if I have 2 flags, that means that I start off with 6. So I would have 6 choices for the first flag, 5 choices for the second, which is 6 permute 2. It's equal to 30. You can have 6 flags. For the first one, you'll have 5 choices for the second flag and 4 choices for the next. So it's 6 permute 3. So there's 6 choices and we're going to pick 3. So we have 30 times 4 gives you 120. Whoops, there it goes. Okay, then over here you would have 6 times 5 times 4 times 3. So that would be 6 permute 4. You'd have the 120 times 3, so that's 360. Times 2, which is 6 permute 5, or 720. And lastly, you would have 6 times 5 times 4 times 3 times 2 times 1, or 6 factorial, or you could think of that as 6 permute 6. And that's 720. Okay, so what you would do then is, because you have 2 flags or 3 flags or 4 or 5 or 6, by the sum principle, because of this or, I just simply add them up. So I have 720 plus 720, which is 1440, plus the 360 gives me 1800. And then you add on the 120, which is 1920, plus the 30 gives you 1950. So just adding them all up. So, therefore, there are 1950 ways okay? If you disagreed that, okay, let's say that so what would happen is the order does not matter, then what we get instead will follow the same idea. You would take cases, okay? And then you would say, okay, I have 2 flags, or 3 flags, So with the sum, you would just add up all those cases together. So in this, you would have 6 choose 2. This one, you would have 6 choose 3. This one, you would have 6 choose 4. Over here, you would have 6 choose 5. And lastly, you would have 6 choose 6. And then what I would do, instead of calculating each of those with the, I would use Pascal's triangle. And so I know over here, this would be 6 choose 0, 6 choose 1, 6 choose 2. There we go. So I can quickly count this off. I have 15, 20, 15, 6, and 1. So you have 1 plus 6 is 7, plus the 15 gives you 22, plus the 20 gives you 42, and then lastly you have the 15, which gives you the 57. So adding those up, so you would have 57 ways. If the order does not matter. So you can see that if you add the order in, you get many, many more ways of arranging flags. You have 1,950 compared to if the order doesn't matter. It's saying that, say, this flag and this flag are the same thing, then it's actually quite smaller. You get 57 ways. Is everyone okay with that? Okay, perfect. So let's say for this one, we'll say out of 50 liberals, and 42 conservatives, and let's say 10 New Democrats, how many ways are there to select a committee of 9 members with equal number from each party. So I have 50 Liberals, 42 Conservatives, 10 NDP. How many ways are there to select a committee of 9 members with equal number of members from each party? Okay. Does the order matter then? Because if I tell you that the members are all the same, they're not treated differently, there's no president, there's no treasurer, that's right. It shouldn't have any it doesn't matter in this case. Just to compare with the other one that we had done previously, where we had picked a treasurer and a president with the RMC Flying Club, or sorry, the soccer team, sorry. Yeah, so the order doesn't matter. So that means that what I can do, and what it means that I have equal number of members from each party. So this, the order doesn't matter, so this is a combination. And what I also need to do is equal number of members from each party, which means that there should be 3 members How do you know if the order doesn't matter? So the order doesn't matter in this case because there's nothing to tell me that there's anything in particular special about picking this committee. So the order doesn't matter. No titles given to particular members. What I mean by that is if the order did matter, it would be something along the lines of you're going to create a committee and you're going to have a president, a treasurer, a secretary. And so when you start to do that, well, now you've made labels, you've got choices, and the order then matters. It's if I put this in there, it wouldn't be the same if I change the order. So those 3 members, if I change the order, it changes what the makeup of that committee is now. But because there's no label for that, no treasurer, secretary, treasurer, whatever, the order doesn't matter in which I pick. I just need to make sure that I pick 3 members from each party. To keep an equal number. So that means that I can just slowly start to write this out as I'm saying it. I'm going to, from 50 Liberals, I'm going to choose 3 members. And then, multiplication principle. So then over here is the Liberals. I have 42 Conservatives, and then I'm going to pick 3 of those. And then over here I have 10 NDPs, and I'm going to pick 3. And that's it. On a test, this is what I would expect you to leave it as, because this is quite a large number. Now, what's nice about using this notation over some of the other notations that you might have seen before, some people might be used to seeing NCR or CN, R. What's nice about this notation is that looking along here, I can see that I have 3 plus 3 plus 3, which equals 9. Those are the number that I need to select. So I've made 3 choices. The first one, I made 3 choices on the second, and I made 3 choices on the third. So I've got 9 selected. And that's it. So 50 choose 3. So let's just do this for completeness. So what I can do is I can pull out a calculator. And again, to show you it's quite large. I have 50, and I'm going to permute 3, or sorry, do a combination of 3. So 19,600. I have 42, choose 3, which is 11,480. Multiply that together, and then choose 10, choose 3, which is 120, and multiply that together. It's quite a large number. 27. Is that billion? So again, quite a large. You wouldn't want to see the formulas filled out. I mean, I suppose, well, there's no point in writing out the formula if you're not going to give me a final answer. So what we would say is so like on a test. Okay. And that would say for a specific part or something like that. But again, like as you saw, these numbers are quite large. You know, 50 choose 3, 19,600. You have the 42 choose 3, 11,480. Yeah, that's quite a large number. But something simple like this, where we have 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, 6 choose 6. Those are something that you can quickly calculate, either using your formula, or you could quickly, as we did here, is jot out a small Pascal's triangle. Okay. So here's number 5. Let's say, how many ways can 6 members of the hockey team line up at the blue line so that 2 defensemen are not side by side. Okay, so what is the important information that we have? We have 6 members. They're lining up. 2 defensemen, not side by side. That's kind of the information that you're interested in. So, does order matter? Order matters now, so will we need to make cases? Possibly. Yes, it does matter. All distinguishable. We'll assume so. Okay, and so the defensemen are not side by side. So we know that this is leading to a permutation. And as one person said, we can do this, there's kind of 2 main approaches. We could do it a direct method or direct reasoning. Taking cases. Or what I'm going to do is I'm going to do indirect. So it's all the cases, all the possible ways of lining them up, minus the cases we don't want. Okay. So I think I used an analogy last night when I was going over some of this material, and I said I likened it to a pizza, and it's like it's an all dressed deluxe pizza. There's pepperoni, there's mushroom, there's green peppers, olives, and okay, so that's all the pizza, and you don't want something you don't want. Okay, I don't want mushrooms. Well, take that off. You pick it off, and now you're happy. That's what you wanted. That's exactly what we do with the indirect reasoning. So, with that, I have 6 members. So for all cases, this means no restrictions. How many ways could I line up the 6 members on the blue line then? How many ways can I? Yes, 6 factorial. So that's with no restrictions. Oh, and we're almost, yeah, we're getting there. So that's for no restrictions, right? So I can have 6 choices for the first position, 5, 4, 3, 2, and 1. Then we're going to subtract the cases we don't want. So the cases that we don't want, that's where the 2 defensemen are side by side. Okay, that's having the 2 defensemen side by side is our mushroom. We want to pick that off. So we don't want that side by side. So what does that mean? Well, let's treat them like a single player then. So let's say we have Alex and Bob. So they're A, B. We kind of group them together. We kind of glue them together. So what we'll do is then you treat them like one. So then if in the first position, you would have 5 choices, or 4, or 3, or 2, or 1. So that would be in the first position, the second position, third. Okay? So that's equal to 5 factorial. You also have to consider the other one where they could be BA, because the order does matter. So you would have, again, gluing those together as BA, you would have 5 times 4 times 3 times 2 times 1. So that's another 5 factorial. So those are the 2 cases. I add them together, so it's 5 factorial plus 5 factorial, which is also equal to 2 times 5 factorial, and that's it. Those would be all the cases where I would have the 2 defensemen side by side. So I subtract this, the 2 times 5 factorial. Okay, so I can actually six factorial, that's 720 minus, you'll have 2 times 5 factorial, which is 120. You're going to multiply that by 2 to give you 240. And then subtracting that from it gives you 480. So is there any questions about that one? Looks good. Okay. how about this? Let's say Subway has 8 toppings. Okay. How many ways can you order a sandwich if, let's say, there's no more restrictions, no further restrictions, and let's say must have at least one topping. Okay, so in this case, if we work through our little chart, does order matter? It's a sandwich. It's going into our gut. Goes into our mouth. It all gets chewed up. Does the order matter? No. Good. Nope, it doesn't matter. Okay. Yes, I would like to order a 6-inch with lettuce, please. No sauce, no other vegetables, just, yeah. Can we order all or just some of it? This is where it might get tricky. And what I'm going to say is that basically you could pick just one topping. You could pick 2. You could pick 3. So what that is doing is it's leading us towards all the possible subsets. These are distinct toppings. So it's 2 to the n. Okay, the reason for that is for the first topping, you could have 2 choices. It's either on or off. Yeah, exactly. It's a subset. That's why I'm hungry. slowly the food examples start to slip in. So the first topping. Okay, so you can have it's either on or off for the first topping. It's on or off for the second topping. Dot, 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 all the way down to the 8th one. Two to the 8th. 256. Yep. So there's 256 ways you can order your sandwich. This guy knows binary. Yes. Okay. What I also want to introduce to is, let's do this one. There's another way I can do this. So this is, let's call this solution 1. Okay. And over here, I'm going to call this solution 2. I feel outdated. Okay, so let's do solution 2. So this is thinking about it as putting a topping on or off, okay, all the way up to the 8th topping. How about this one? Now, instead, I could think of it as, here's solution 2. I could think of it as I have 8 toppings, and I choose 0 of them. So over here, that would be I have no toppings. Or I could have 8 toppings and I choose 1 of them. So everyone's not freaking out, right? Like this is, you're like, oh yeah, I could write it this way too. So there's, that's 1 topping. Or I could have 2, or 3, 4, 5, 6, 7, or 8. So what we can do then and start to slowly write out Pascal's triangle. So let me just put this over here. Six plus 15 is 21. And then 15 plus 20 is 35. 35, 21, 7, and 1. And the last one, I have 1. 1 plus 7 is 8. 7 plus 21 is 28. 21 plus 35 is 56. 35 times 2 is 70. And then we... So again, just as a little note, kind of down the center here, oops, you got this symmetry. Kind of like a mirror. So on this side you have 35, 35, and the 21, 7, 1. Same thing here, 15, 6, 1, 10, 10, 5, 1, 4, so on and so forth. So over here, what I have is, this would be A choose 0, A choose 1, okay. So, going back to this, what I want is now this whole row right here, which I've done now. So I have 1 plus 8 plus 28 plus 56 plus 70 plus 56 plus 28 plus 8 plus 1. And what I'll do is I'll write on this card over here what the answer is. Oops, maybe I won't put it on that one. Here, I'll put it on this card. So, can you tell me what the sum is for this? Is there a correlation between probability distribution and the values of those center sums being the highest? It looks a lot like a bell curve. There is, yes. There is a correlation. Mm-hmm. Yep. What you should do, Mr. Puffin, is to check out I think it's almost probably the last section of the book, which is about the normal distribution, and you'll see that there's a little how the kind of binomial coefficients kind of lead their way to being a normal distribution. Exactly, 256. Good. Which, hello, that's great. 256, 256. So surprisingly, what we've got here is that it's almost like he knows what he's doing. Yes, almost. Almost exactly. So, if I go back here, if I sum all these up, so that's the 8th row, 2 to the 8th. That's 256. If I wanted to go, let's say here, let's add these up. 1 plus 4 plus 6 plus 4 plus 1. That's equal to 2 to the 4th. So 2, 4, 8, 16. So what if you have the nth row, the sum of them is equal to 2 to the nth. Okay, so basically what I did was I did a combinatorial proof for you. Again, I counted it in two different ways. In the first way I had done it, which is solution 1, I said I could have the topping either on or off, and then the next one is on or off, and all the way to the end. That gets me to the 8th. Okay, so that was one way of counting it. The second way of counting it was I could use combinations. So I have 8 choose 0, or I have 8 choose 1, or 8 choose 2, all the way up to 8 choose 8. Again, these are all the cases. So 1 plus 8 plus 28, blah, blah, blah. I can add those all up, and I get 256. So it's the same thing. Here's 8 choose 0 plus 8 choose 1 is equal to 2 to the 8th. So I've counted it. This is from solution 2. Here's solution 1. And I get the same answer, 256. So in general, what I have is n choose 0 plus n choose 1 plus n choose 2 plus ... all the way up to n choose n is equal to 2 to the nth. Okay, so you're going to be saying, well, like whoop-de-doo. You know, how's this going to help me? Well, this helps you actually in the next question. So because we have up here, it says must have at least one topping. And you're thinking, okay, well, I have this. Do I have to do any weird calculations again? So here's B. Let's say must have at least one topping. Okay. So what I'm going to do is I'm going to copy this down again. So over here, I would have 8 choose 0. So that's no toppings. Plus, I'll have 8 choose 1. That's one topping. Plus, let's say 8 choose 2. Dot, 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 all the way up to 8 choose 8. And I know that this total is, from over here, 256. Now, what I want to do is count where I have at least one topping. Well, would be 2 to the 8th, yep. Let's move this to this side. So I would have 8 choose 1, 8 choose 2, ... all the way up to 8 choose 8. It's equal to 256. And I'm going to bring this over to the right-hand side. So now I'll have 256 minus 8 choose 0. And there's only one way, so 8 choose 0, there's only one way to do this. So it's 255. Yes, exactly. So here is thinking about it like indirectly. All the possible ways. Minus 1, which is the one case with no toppings. And so you can think of that as the indirect. So, therefore, there's 255 ways on a sub. So you can keep pushing this further. You could say where it must have at least 2 toppings. Which means then that, okay, so I would have a choose 0 plus a choose 1 plus a choose 2. So what I would do is I would bring over this case in this case over so that I would have a choose 2 plus a choose 3 and so you would use a choose 0 minus a choose 1. And so a choose 0, there's only one way to do that. There's 8 objects and you're going to pick one. There's 8 ways to do that. So that's 256 minus 9 gives you 247. So what's very nice about this kind of math is that there's not necessarily one way to solve it. Okay? We could do it directly. We can do a direct method. You could count it indirectly. You can, as you saw, I could be thinking of it in terms of subsets, or I could be thinking of it in terms of combinatorics, like a combination, and adding them all up. It's really important to decide whether or not the order matters or doesn't matter, because we can be orders of magnitude off. But sometimes we don't, you can, the permutations can be reduced to just using a multiplication principle. So again, what we're looking for when you're solving a counting problem is to make sure that whatever you're doing, that it's reasonable, that you're telling us how you're counting it, that if you make an assumption, like something like this, where you assume that the two flags are different meanings, that these are all reasonable. Oh yes, and here we go. There was the symmetry property. Here was 8 choose 2, and there's 8 choose 6. So again, if we had the 8 points and we select 2, there's 8 points and we didn't select 6 of them. Again, if we look over here, there was the 8 choose 2, the 28, and then there's the 8 choose 6, again, the 28. So again, I could pick 2 objects, or the mirror of this would be not picking 6 of them. So I would say a good question to look at, if you haven't done it, assignment 6, look at the last question. About City Hall. And you'll be able to solve this in at least 2 different ways. The other thing to mention is that assignment 7 is posted. And in this, you'll get to explore more properties of Pascal's triangle. And of course, we have our test on Friday. We have Zoom office hours tonight. Okay. Okay, is there any more questions before we sign off for today? Okay, without any further questions, thank you everyone for tuning in for today's lecture on an approach to solving counting problems. Sir, with regards to the test, I know a large number of people now have roommates, meaning the microphone on policy may be an issue. Is there any plan for this? I will have to consider this. But you should be you'll have to be able to work in a room that is quiet, and that would be disruptive if somebody is talking the entire time. So we'll have to discuss this. Office hours are at 7 p.m. Eastern Standard Time or on RMC time. And again, okay. So send me, if there's any more concerns about the test, please feel free to send me an email. And with that, have a good night. Yes, exactly. That's what I've done before. Just keep the volume on low, and if I need to speak/yell, I'll do that. Yes, and there's computer labs. Thank you, and have a good night.